Hello, this will be a demonstration of Proposition 9 from Book 2, which states that if a straight line be cut into equal and unequal segments, the squares on the unequal segments equal double of the square on the half plus double of the square on the straight line between the points of section. Points. Again, classic Book 2 enunciation, not at all obvious, but so let's work with an example. So all we are given is a straight line, AB, this is usual, and we have a point C on it such that AC and CB are equal, and then we have some other point on it, D, such that AD does not equal DB. Okay, and that's all we're given. Now, what we have to set out to prove is that the squares on the unequal segments here being AD and DB, and so we're trying to prove that the square on AD plus the square on DB equal double the square on the half, in this case just AC, so equal double the square on AC plus double the square on the points of section. Well, the points of section are C and D, and so the straight line between them is CD. And so we're also going to be working with double the square on CD. Put that all together. The square on AD plus the square on DB equals double the square on AC plus double the square on CD. This is what we have to prove. First, from point C, let us draw the straight line CE perpendicular to AB, like so. We shall also make CE equal to AC, like that. And as a consequence, it's also equal to CB, because AC and CB are equal. Next, we simply join the straight lines AB and, not AB, AB already exists. We join the straight lines AE and BE. So, these straight lines exist now. This is postulate. Oh, should have explained. The perpendicular line step, proposition 111, because the point's on the straight line. And then making it equal, that's 1-3. This is a classic technique Euclid uses all the time. Joining straight line between 2 points, simply postulate 1. Now, through point D, we're going to make DF, DF here being the point at which EB and the straight line through D intersect. We're going to make DF parallel to EC. So these straight lines are going to be parallel. And then we are also, through point F, going to make FG such that the point G is the point at which EC, the straight line through F, intersect. We're also going to make FG parallel to AB. The final step, we simply connect the dots. We make the straight line AF. This is again postulate 1. And we're done with our construction. It's a nice change of pace. I miss working with triangles. We've been working with squares for like 8 propositions in a row. So nice to see our old friends back. Now, because, let me try and work this out real fast. Ooh. Oh, wait, that's my bad. Those are equal. So we know that AC and CE are equal. We know that they're equal because we made them that way. And therefore, the angles which they subtend, namely angle EAC and angle AEC, are going to be equal. This is proposition 1-5. We're dealing with an isosceles triangle. We're dealing with the triangle ACE, and the equal sides are AC and EC. And so the angles which subtend them, here being EAC and AEC, are going to be equal. Proposition 1-5. Now, we also know that angle at C, give me one moment to figure this out. I see. Okay. So, we're working with the triangle AC. Now we know that the angle at C is a right angle. We know this again because of step 1. We know that this is a right angle. And so because the interior angles of a triangle always add up to 2 right angles, this is proposition 132, if one of the angles be a right angle, then the other 2 must add up to a second right angle, so as to satisfy proposition 132. And so because we know that the angle at C is a right angle, we can then say that the sum of the 2 remaining angles, here being EAC and AEC, add up to another right angle. We also know that they're equal, right? We showed that by proposition 1.5. And so if we know that 2 things which add up to one thing are equal, then we know that each thing on its own will be half of what the sum equals. It's a bit of a weird way to word it, but this is all to say that because we know that EAC and AEC add up to a right angle and each of them are equal, we know that they must be half of a right angle. And so we can say that EAC equals half of a right angle. We can also say that AEC equals half of a right angle. This appears to be common notion 3 to me. Similarly, we can also prove that the angles CEB and EBC are also equal to half a right angle. We can go about this in a similar way, showing that because CB and CE are equal, we can say that the angles which they subtend are also equal. And in the triangle ECB, one of the angles, the angle at C again, different angle at C, but it's the same thing. We know that the angle at C in this case is also a right angle. And so the 2 remaining angles, CEB and CBE, must also add up to 1 right angle. And if they're equal, each equals half of a right angle. And so we can then say, if we add these equals to equals, we can say that if we add the angle AEC and the angle CEB, so if we add this angle here and that angle there, and this is simply going to give us the whole angle AEB. Because each of its parts add up to half a right angle, if we add 2 halves of a right angle up together, we're going to get a full right angle. And so we can say that the angle AEC plus the angle CEB, that is to say the angle AEB, equals a right angle. Not merely equals, it really just is a right angle, but semantics. Now, we know that the angle GEF equals half of a right angle. We know that the angle GEF equals half of a right angle. GEF is just the same as the angle CEB. So we know that's half of a right angle. And we also know that the angle EGF is a right angle. How do we know this? Well, we know that GF and CD are parallel. We made them that way in the first step. And so the corresponding angles are also going to be equal. In this case, the corresponding angles we're talking about are GCD and EGF. And we know that the angle at C is a right angle, and so whatever it's equal to will also be a right angle. And so we can say that the angle EGF is also a right angle. We can therefore say that because we know that in this one triangle we have one right angle, we have one angle that just is a right angle, we have another angle that equals half a right angle, the remaining angle such that all 3 add up to 2 right angles must simply then be another half of a right angle. And so we can say that the angle EFG is also half of a right angle. Now both EGF and EFG add up, or not add up to, both equal half of a right angle, and so these angles are equal. And so because of proposition 1.6, we can say that the sides which subtend them are also equal. In this case, we can say that GF which subtends GEF, is equal to EG, which subtends GFE. Again, this is proposition 1.6. Similarly, we can prove that FD right here, is equal to DB. We can do this by showing that, again, by corresponding angles, we know that the angle at D will also be a right angle. We know that in this triangle, we have one right angle, we have half of a right angle, and so the remaining angle must also be half a right angle. In this case, that will be DFB. And so we have two equal angles, DFB and DBF. And so the sides which subtend them will also be equal. In this case, that is to say that DF and BD are equal. So that's how we get to that. Next, because AC is equal to CE, and we know this because that's how we constructed them, this is the first step, we can say that the squares on them will also be equal. This is a property of magnitudes, that the squares on equal straight lines will also be equal. And so we can say that the square on AC is equal to the square on EC. And so again, in a similar move to what we've seen before with common notion 2, we can say that AC squared plus CE squared equals double AC squared. We also know by proposition 147, I believe this is the second time this is used, because there's prop 148 that everyone kind of forgets about. So using prop 147, the Pythagorean theorem, we can say that the square on EA is equal to the sum of the squares on AC and CE, because this angle at C, again, is right. And so we can say that EA squared equals AC squared plus EC squared. And so we can also say that the square on EA squared, will also equal double AC squared, because AC squared plus EC squared equals double AC squared. And so we can say that whatever so this is common notion 1, both EA squared and double AC squared are equal to the same thing, AC squared plus CE squared. And so we can say that they're equal to each other, that EA squared is equal to double AC squared. Again, similarly, we can show that the square on EF is also equal to double the square on GF. Again, going through that real quickly, we know that GF and EG are equal, and so the squares on them will be equal. And so we can say that EG squared plus GF squared equals double GF squared. We also know that EG squared plus GF squared equals EF squared. And so we can say that EF squared equals double GF squared by common notion 1. Awesome. Now, we know also that GF is equal to CD. We know this by proposition 134 because we're dealing with a parallelogram, GD. And so the opposite sides, in this case GF and CD, will be equal. So we can say that GF is equal to CD. And so we can substitute this GF here for CD, and we can say that the square on EF equals double the square on CD, because CD is equal to GF. This is again a property of magnitudes, where you can substitute the side of a square for an equal length. Now adding equals to equals, common notion 2, we can say that the square on AC, EA squared, square on, I might have said AC. Anyway, the square on EA squared, plus the square on FE squared, is equal to double the square on AC and double the square on CD. This is again just adding equals to equals, common notion 2, we've used this plenty. Furthermore, we know that AE squared plus EF squared will equal AF squared. So we're now dealing with this triangle. So right here, we know that that's a right angle. We know that the angle at E is a right angle, or at least that angle at E is a right angle. And so we're working with this length here, AF squared, which is the side subtending the right angle. the square on that side is going to equal the sum of the squares.
Hey, we're a mask.
Understand.
Even though there's nobody around. I don't make the rules.
Okay, so. Mercy. We can, because we know that EA squared plus EF squared is equal to AF squared, we can say that AF squared is equal to double AC squared and double CD squared. Now, again, working with another triangle, switching to another right triangle, we can say that AF squared is equal to AD squared plus DF squared. Again, proposition 147. We also know that DF and DB are equal, and so we can say that the square on AF equals the square on AD plus the square on DF is equal to the square, mercy. Yeah, we can say that the square on AF is equal to the sum of the squares on AD and DB. So we can say that AF squared equals AD squared plus DB squared. And so we can then say that the square on AD plus the square on BD is equal to double the square on AC and double the square on CD, because both are equal to AF squared. Now, this final statement here is what we set out to prove, that AD squared plus BD squared equals double the square on AC and double the square on CD. And so this being what was set out to have been proven, we are done with the proposition, therefore, etc., QED. I do not have anything to say about this proposition. It's nice that we got to work with triangles again, a little bit different, but that's all. So I will see you guys next time for Prop 210.